Right, we'll start. Good evening, everybody, online and in the lecture theatre. Welcome and thanks everybody for attending this evening. My name is Charles Dwyer. I'm chairman of the Water and Environmental Society of Engineers Ireland. Tonight we are hosting a talk on the Nant de Drance, you'll have to excuse me, hydropower scheme. It's basically a 900 megawatt, 1.6 billion euro project. Tonight's speaker is Patrick Heck. He's kindly come over from Switzerland actually today to be with us, so thank you very much. He's a chartered civil engineer, civil and environmental engineer, and he's working as a project manager currently with BG Hydropower. That's correct, isn't it? What I'll do, just before we start, I'll ask you all to turn your phones off and on silent, and I'll welcome Patrick to the stage, and then we'll have, it'll take about 25-30 minutes for the presentation, and then at the end we'll put some questions to the floor if you guys want to ask or have any queries. He'd be more than happy to answer them. All right, so you might put your hands together for Patrick, please. Thank you very much.
All right, thank you, Charles. Good evening, everyone, and hello to everyone online. So the story I'm going to tell you about tonight is the story of the Nant de Drance hydropower scheme, which is a pumped storage hydro scheme in Switzerland, and how it's going to fit into the Swiss and the European grid. So first of all, a little bit about myself. I'm a civil engineer. I graduated from Trinity 10 years ago, and I left Ireland straight after that. Worked in the UK for a couple of years as a geotechnical engineer, and then I joined BG Consulting Engineers in Switzerland in 2010, and I was there ever since. I had crazy ideas about going off to Hong Kong, Singapore and all that, but that clearly didn't happen. But it's okay actually, because I'm now working as project manager for the civil structural part for the caverns on the Nant de Drance hydropower scheme. So this is the structure of my discussion this evening. First of all, I'm going to go from the general to the particulars. So first of all, a little bit about energy storage in general, then about pumped storage hydro specifically in an international and then in more of a Swiss context. And then I'm going to go to the Nant de Drance project itself. I'm going to show you the existing hydropower scheme. There's about 100 years of hydropower in that valley, and then how the Nant de Drance scheme kind of superimposes onto the existing. And then finally, I'm going to look at a few particular technical challenges, what we did underground, the access tunnels, the main caverns, the pressure shafts, etc. And then also the structures which we build outside, namely the downstream intakes and the dam heightening of the upper reservoir. And just finally, quickly, I'll touch on a couple of logistical issues. So first of all, energy storage, a hot topic in 2017. Just looking in the media over the last month or so, you can't help but see that everyone's talking about clean energy and the various challenges it's going to pose. Namely, the Economist had a special report about it 2 weeks ago, and what I took from all these articles was that the main challenges were how are we going to store all this clean energy, because it's produced intermittently, and it's not necessarily produced where you want it. So we're going to need to store it and we're going to need to move it. So storage and interconnectors were the main thing. Then the ICE also produced recently a briefing on pumped storage specifically, because the UK are planning to double their pumped storage capacity over the next few years. There's quite a lot of projects there on the shelves. And finally, NCE magazine did a whole thing last month about energy storage, and they were waxing lyrical about power banks and what Elon Musk was going to do to revolutionize energy storage in the household, but there was not much about pumped storage. So just putting energy storage into context, I found this maturity chart in a policy paper by SSE Renewables, which I thought was quite good. And essentially it shows you where we are right now. So Elon Musk is up here somewhere. Then the compressed air storage system, which NC magazine was talking about, is there. So it's, you know, coming to the final stages of deployment. And pumped hydro is, you know, well underway. So it's a well-known technology. It's mature. It's highly efficient, and you can quickly store or generate large quantities of energy. So this is the energy storage chart. How do you say? It's the installed global energy storage worldwide, and we can see that over 99% of it is pumped storage hydro, and just that little bar at the top is all the rest. And this is another graph which I found, which shows the evolution of pumped storage hydro in the world over the last 70 years. So what interests us here is Europe, over here. So we saw that we had a kind of quite strong development up to 1990, and then things tapered off before kicking off again in 2010. And so I reckon this new enthusiasm has something to do with the development of renewables, namely wind and solar power in Europe. There's another thing is that this jump we can see from 2010 in Europe is about 5 megawatts or so, and that can directly be attributed to a handful of installations which are namely being constructed in Switzerland and in Germany. So this is the current pumped storage situation in various countries in Europe. So all there on the left we've got Turlock Hill. That gives you an idea of where we are in Ireland. That's where Switzerland is. And because it's not necessarily easy to find a good comparison, I would suggest we compare it to what's going on in Austria. So Austria is just 2 over here. I can see that Switzerland finally isn't that well equipped, especially in terms of pumping. So pumping is on the right and turbining is on the left. And this discrepancy which you see in Switzerland is probably due to the fact that a lot of the pumps on the pumped storage hydro systems were installed later. They were retrofits, essentially. But all this is changing at the moment. So in Switzerland, currently there is quite a large appetite for pumped storage hydro. So there are 3 big projects going on or that are nearing commissioning or being commissioned at the moment in Switzerland. So we have this one here, which is FMHL+, which is a 400 megawatt one. We have the one I'm talking to you about tonight here, Nant de Drance, which is 900 megawatts. And we have another one all over here, which is Lint-Limon, of a power of 1,000 megawatts. As well as that, there are a number of other ones on the shelves. There's another one down here in the Rhone Valley. There's another one over there near the Italian border, and another one right in the center there. So all in all, there's 2.5 gigawatts of pumped storage coming on stream over the next 2 years, and there's possibility for another 3 in the next 5 to 10 years, depending on the economic viability of it. And just while we're looking at this slide, a quick geography lesson. So 80 to 90% of the Swiss population lives here on the Swiss plateau. It's where you have all your major cities, and this is where all the hydropower is produced. So you have to get all the energy up there. So what's driving this appetite for pumped storage in Switzerland? So there's one thing, it's the development of clean energies. That's kind of a global cause, but I would suggest there are also 2 major Swiss causes, and the first one is this. It's Swiss energy policy. So currently they're developing the energy policy for the next 30 years in government, and the following points are of direct relevance to pumped storage. The first one is developing interconnectors to better serve nationally and internationally the European grid. And the following 2 points is on the right-hand side, development of renewables, so wind and solar, and finally nuclear decommissioning. So currently there's no deadline, as in other countries, as to when Switzerland is going to decommission its 5 nuclear power stations. But since they're in midlife, it's going to happen probably over the next 20 years or so. So here's a simulation of energy consumption, electrical consumption in 2015. And what you see here, you have band energy here being produced by the nuclear power stations. You have some more here by the run-of-river. And then up here, the red spikes is the energy contributed by pumped storage. So you see there's a limited amount. Now fast forward 20 years to 2035, and this is what the situation looks like. So nuclear power stations have been switched off, and demand has increased. And what you see is you need a lot more pumped storage, also to serve the export market down here. So this is one of the reasons why Switzerland is all of a sudden getting into this pumped storage. And this is the second Swiss reason why pumped storage is of direct importance at the moment, and that's the Swiss Federal Railways. As you know, Switzerland is pretty much fully electrified with the railways, and each one of these is about 10 megawatts, give or take. So when they're going up a hill, they're pulling 10 megawatts off the grid, and when they're going down the hill, they're putting back 6 to 7 megawatts. So there's that, and there's also the fact that the Swiss timetable is on a half-an-hour basis. So every half an hour, a whole load of trains are leaving all the major cities. And a half an hour later, or an hour later, a whole load of them are arriving into the stations. So what you see is, on a daily basis, the consumption of the railways is about equal to the city of Zurich, a city of 1.5 million people. However, your variations during an hour are about 120 megawatts. So that's why the Swiss Federal Railways are also quite interested in pumped storage, especially if you can switch it on and off very quickly. So now that you have an idea of the Swiss context, so let's move on to the site of Nant de Drance. So Nant de Drance is situated on the village of Fin-Haut, which has had, intensive hydroelectric development over the last 100 years, starting with the Swiss Federal Railways in the 20s, the 50s, and then a large international Swiss-French hydropower scheme called Emerson in the 60s and 70s, and finally today, Nant de Drance, this new pumped storage system. So just people who don't do skiing among you, it's situated between Martigny and Chamonix, here on the French-Swiss border. So this is a picture of Barberine. This was the first dam which was built on the village of Fin-Haut in the 20s. It was a form of Marshall Plan by the Swiss government, since there was an economic crisis going on at the time. And the Swiss Federal Railways had decided to electrify all their network after the First World War, when they couldn't get coal. So they decided to build this very large power station at the time, so with a single curvature arch dam, 80 meters high, 40 million cubic meter reservoir, and 220 megawatt station, so it's quite big. And then as things went on, electrical demand for the railways continued. So Swiss Federal Railways first started drawing water from a nearby valley, before in the 1950s damming it up with the dam called Vieux-Émosson, which is 400 meters higher than Barberine, with an additional 10 million cubic meters of water. And then finally, in the 1960s, EDF, which is the French electricity utility, and ATEL, which is the Swiss one, decided to get together and create a really large reservoir just a little bit downstream from Barberine. This is the original dam built in the 20s, and this is the dam built in the 60s and 70s here, Émosson. So they created with that, by drowning Barberine, the second largest artificial reservoir in Switzerland. Just an interesting fact about this, it was situated on the border, So in order to construct it, France and Switzerland had to do a land swap, which was signed by Charles de Gaulle himself in the late 60s. So this is a synthetic view of the existing hydropower installations. So you have two systems running in parallel. You have the Swiss Federal Railway one, which has a power station in Châtelard and another one further down the valley down in Vernaya. And then overlaying on top of that, because of this new dam in Émosson, you have the Émosson SA scheme, which runs another one in another power station in Vallorcine and another one down at the Batia down here. And so this is a plan view of the scheme. The key, if you will, is Émosson Dam. And then you have a load of collectors which go and collect water in nearby valleys. You have both in France and Switzerland, I might add. You have also a particular one, it's a collector which goes underneath the glaciers around Chamonix. So you have the Glacier d'Argentière, Glacier du Tour, and another one, the Lorgnon. So coming on to Nant de Drance pumped storage hydropower plant itself, what's the idea? The idea is to do pumped storage between the two existing reservoirs here. So Émosson, the large one, and Vieux Émosson, the small one. Who wants to do this? So the owners are Alpic. It's the Swiss utility which created Émosson back in the day together with EDF. They're the majority shareholder, also the Swiss Federal Railways, as I was telling you earlier on. And we have two minority shareholders, the FMV, which is the local utility of the Valais region, and Basel, which also had an interest in it. The civils contractor for the works is GMI, so it's a joint venture between the two largest contractors in Switzerland, Marty and Implenia. Overall project cost is about 2 billion francs. It's been a slight cost overrun since I gave you my previous estimation. And construction program is 2008 to 2019. In terms of the consultants involved in the project, so we have AF Consult, which was Motor Columbus before being bought, and they're quite a famous name in the world of hydropower. They're the lead consultants. BG, that's ourselves. We're looking after the civils for the caverns, as well as the HVAC for the whole installation. SRP are looking after all the management of spoil, how to reuse the spoil and how to manage it. And POIRI are looking after all the waterways. In terms of the contractors, we have GMI, as I was telling you earlier on. They have the lion's share in terms of all the civils. GE was Alstom before they were bought over. They're looking after all the machines inside the cavern. Andritz Hydro are looking after the waterways. And ABB are looking after the electrotechnical stuff, so all the converters and stuff like that. The switch gears and all that are in a separate contract. It's directly Swissgrid who are looking after that, but Siemens is the lead contractor for those. In terms of the key characteristics of this installation, it's a 900 megawatt pump storage scheme, so 6 reversible pump turbines, Francis, and they're asynchronous and variospeed, so they're quite particular. The head you have to contend with is between 250 and 295 meters, which is also a bit particular. It's highly variable. There are 2 parallel waterways, each of which can handle 180 meters cubed per second. So just to give you an idea, 180 meter cubed is what a normal household uses in a year, so it's a lot. And the other figures I've mentioned already, I think just another one is the length of the concession. So they have an 80-year concession on the waterway between Vieux Émosson and Émosson. So this is a cross-section of the hydraulic system. I suppose we should start with the wet tunnels. So up here, this is Vieux Émosson Dam. It's been heightened by 20 meters in order to double the volume of the reservoir. So was 40 meters high, is now 60. We have the adits coming here up to the butterfly valves. We then have 2 parallel 400 meter high pressure shafts, which then bring the water into the main cavern, where we have our six units. And then we have the tail race, which comes here to the downstream intakes. So this is the variable head difference. This depends on how full the lower lake is and the upper lake. So you see it varies between 250 and 375. And then if we're looking at the dry tunnel systems, this is the access tunnel from Le Châtelet. Just to remind you, this Émosson is at about 1,950 meters, and Vieux-Émosson is at about 2,200. So they're very difficult to access in the winter. The idea is that we can access all year round to see all the various installations. So we have this 5.5 kilometer long access tunnel to here, and then we have another access tunnel which brings us up to the other components up there. This is an overall view of the installation. So Nant de Drance itself is focused here between Émosson Lake and Vieux-Émosson. And this is the access, the all year round access here from Le Châtelet, which has an altitude of 1,100 meters, and the 5.5 kilometer long access tunnel, which is here. This is a 3D view. You know, it's always a bit hard to see what's going on, either on, you know, having a plan view or cut. So a 3D view is always a bit helpful. So we have Émosson Lake here, Vieux-Émosson Lake up here. Powerhouse caverns are down here. The butterfly valves are up here, and this is the tunnel that goes up all the way. And this is an intermediary access to the lower dam. In terms of the ground conditions, it's quite typical of that area of the Alps. We've got a little bit of carboniferous down here, followed by some granites. And then we have some metamorphic rocks here, metagrauwakes, and gneisses, which are here. Generally quite good conditions. This is the geological cross-section at the caverns. So we're in the gneiss area, and the caverns were located so that they are perpendicular to the dip and dip direction, which is favorable for the lining design. So the main access tunnel is 5.5 kilometers long. It was excavated using a 9.5 meter diameter hard rock TBM with an open shield. It's the same one which was used for the Lurchberg base tunnel. So it's dug quite a few kilometers of tunnel. The start of excavation was in the autumn of 2009. Here we have a follow-on trailer. All in all, the length of the tunnel boring machine was about 400 meters, with all the various bits and pieces that go behind. And this is once it got to the top. It's a picture of the guys overhauling the cutter head. So this is we saw it earlier on, this is the profile of the tunnel. So it kind of goes out of the way. It's not the direct route from Le Châtelet up to the main hall cavern, and that's because on one hand we needed to maintain a constant slope of 12% to get to the top, and on the other hand we didn't want to go and undermine the existing dam here, which is 180 meters high, and it's quite sensitive to settlements. So this is the advancement curve, and I think it's quite interesting because you can see the effect of the geology on advancement. You see here we're in the granites, advances quite nicely. We get into the metagrauwakes, which is more slaty, so it's a bit more complicated. And then finally we're into the gneisses, and there we go again. Finally, one particular challenge with that tunnel drive was a fault, La Faille de la Veudale, which is here, which is right next to the left-hand side foundation of Émosson Dam. So we had to go through that area without undermining the dam. So that was a finally it happened quite well. We didn't have too many issues, but we did have to carry out 9 months of injection grouting all the same to reduce the water inflows. Then moving on to the caverns. The caverns in themselves are quite large. They were, at the time, the largest in Europe and some of the largest in the world. The powerhouse cavern is 50 meters high, 30 meters long, 30 meters wide, and over 200 meters long. So that would house all those machines. And there next to it is the transformer cavern. And so there you go. That's a long section of the powerhouse cavern with the access tunnel, which arrives here. We have mounting places here and over here, and there are 6 groups. And just a couple of words about the machine itself. So as I was saying, it's an asynchronous various speed Francis pump turbine, vertically mounted. And one of the particular features of this is that it has a spherical valve above and below. And the reason for the spherical valve below is the very high downstream pressures due to the level in the lower lake. So that's something which is quite unusual. Another thing which is quite exceptional is the weight of this of the alternator. It's about 300 tons. So the cranes, we've got 2 cranes with a specified working load of 180 tons, which can be coupled together. So here are a few pictures of the excavation of the powerhouse. We started with the crown and then worked our way down. And before we went too far, we had to concrete the arches because that was the last time where we could actually access the roof. We concreted the arches, stuck them on pre-stressed anchored whaling beams, and then went all the way down. And this is a picture in December 2013 for St. Barbara Day, which is a big day for miners. So no work and big feast. And then when we were at the bottom, we had to go all the way back up with the concreting works. So that's a picture of one of the concreting stages at level 0. It's a 1 meter thick slab with a specified working load of 100 kilonewtons per square meter. So it's quite something in terms of structure. And that's a picture at the end close to handover. So handover of the structure inside the main hall cavern was in the summer of 2016. Another buried structure which deserves a bit of attention are these 2 vertical pressure shafts I was showing you earlier on. They're over 400 meters high, and they were excavated by raise drilling. So the way this is done is there are 3 steps, although you can only see 2 on this picture. First, you drill a pilot borehole all the way down to make sure you're well aligned. Then you attach a drill bit and you pull all the way back up. So this was carried out by a specialist contractor called Östustettin. They're an Austrian outfit, and they do a lot of this. So first of all, this is where the pilot hole the pilot boring was supposed to come out. So you can see it came out quite well. And there you go. Second, you attach your drill bit, which was a diameter of 2.5 meters, something like that, onto your drilling rods, and you pull it all the way back up. And you hope that 400 meters on top, you still have a drill bit. And finally, that's the last stage. From the top, we went down using the traditional drill and blast method to widen them so that we could have finally an inner diameter of 6.5 meters. So this is an excavator which is sitting on top of the hole, and this is a view from on top. And the excavator essentially takes all the spoil and sticks it in the hole, and it's then collected. The mucking happens at the bottom. So it's a very brave man who earns his wage in that digger. All this underground work was recognized by IC and ITA. They organized the annual tunneling awards, and we won the award for large international project back in 2014. So this is all the bosses going to London for food, and this is us on site with the trophy. So 95% of this project happens underground. You're not going to see it, but it doesn't mean that what goes on outside is uninteresting. So I've selected a couple of things which may be interesting for you, namely, this is the downstream water intake. It had to be constructed with the constraint of the lower lake being operated. So at the start of the season, the lake is quite low, and then as summer goes on, etc., the lake goes up until the end of the summer when it's at its highest level. So while the excavations could take place quite quickly, the construction of the intakes was going to be more problematic. And that was solved by doing an immersed tube type thing. So while the contractor prepared the landing zones for the intakes themselves were concreted close to the top water level next to the existing dam here. And then they were, at the end of the summer, floated over and sank in their final location. So this is what happens, right? They were jacked up, well, they were lifted up on a barge, floated across, and then put down, and a guiding pin left on site so that we can make sure that they get put in the right place. So this is the construction of one of them. The picture is unfortunately a little bit stretched, so it overestimates a little bit the height, but nonetheless it's quite an impressive piece of engineering. And also we see the back of Emerson Dam and the original installations which were there for the construction of the dam back in the 60s. And these are the dimensions of the water intake. So it's a 3-story building and 10 meters high, and 25 and 22 meters, give or take, in planned dimensions. And this is a picture of them being floated over into its final location. So the intake is underwater. And this is a good picture. It shows you the path of the intake, and then it was jacked down 100 meters into its final location. And there you see the top water level for the dam. And the final, exposed structure I want to talk to you about is the dam at Vieux-Emerson. As I was saying, in order to double the volume, we had to heighten the dam. So originally it's a single curvature, not reinforced, but it's a single curvature concrete arch dam. And the idea was to cut it down a little bit, change it into a double curvature arch dam, and bring it up to a height of about 60 meters. So this is a picture in 2012 when they opened the site in April. So generally they're the kind of conditions you want when you go skiing, but not when you want to start a site. So they prepared the installation in place. You can see the dam, nice and sturdy concrete arch dam. Then demolition began in the summer of 2012. And you can see they're actually using road milling machines in order to demolish it. They started off with another method and then realized that this was probably the more efficient way to do it. And finally, they concreted alternating steps all the way up till they reached the final level. And this is a good picture of the heightening. You can also see the work being done on the upper intakes here. And at the bottom there, you can see the lower lake quite full, as you can see. And this is the situation last summer. We went for the IC Swift section visit to Nant de Drance. So this is Brendan Quigley, for those who know him. It's another paddy. And as the dam's finished, they're only finishing up the injections and putting a bit of coating on the upstream side. Finally, a couple of words about muck management. So this site created about 4.5 million tons of excavated spoil, of which about 15% was reused as concrete aggregate, and we had to find somewhere to put the rest. So to that effect, 4 repositories were opened in order to stock all that. A rock crushing plant was set up on site in order to produce the various aggregate fractions needed. And this was quite an elegant solution. They used the spoil, which is no longer used, in order to repair damage which had been done to the site previously. This is a quarry which had been opened to construct Émosson Dam back in the 60s, and now it's being backfilled and it's been, replanted in order to cover the damage. And this is my last slide. It's to do with the logistical challenges. Nant de Drance is like building a ship in a bottle with a 5.5 kilometer long bottleneck. But as well as that, you have to contend with very adverse weather. So in places up to about 10 meters of snow. And no matter which way you come, either France or Switzerland, you've got a mountain pass to cross. So it's something which adds cost and complexity to an already very complex project. So there you go. Thank you for your attention. And I guess we can open the floor to questions.
Does anybody have questions? Patrick, I'll give you a microphone there. Sorry.
Hello?
Yeah. Patrick, I wasn't quite clear. How many pump turbine units are there in it?
There are 6.
Oh, 6, yeah. So is it 3 on each of the vertical shafts?
Exactly, yeah.
With a manifold at the end, is it? Or how are they fed from the vertical shaft down to?
There's there are 2 waterways coming down,
Yeah.
right? And then there's a 90-degree angle, and then there's it branches out into 3.
Right.
And at the end of each one, there's a spherical valve just before you go into the machine.
All right. Okay. And the diameter of the main shafts coming down?
6.5 meters inner diameter.
And are they lined or are they?
They're lined at the direction change points. So at the bottom, there's about 20 meters of lining, and then the rest it's concrete.
Right. Thank you.
It's just for the people online, sorry.
Thank you, Jim Casey, OPW, Patrick, and thank you for a very interesting presentation. I have 2 questions. My first question is, 20 meters on top of that dam is quite a lot of additional hydrostatic load on the lower levels of the original dam. Did you have to do any strengthening or grouting work to that existing structure to, strengthen it against that? And my second question, could you tell us a little bit about your the nature of the contract? Was it a remeasurement contract? Was it FIDIC, or a little bit of background on the type of contract that you're using there in Switzerland?
With regards to the heightening of Vieux-Émosson, it was quite conservatively designed to begin with. So there was some grouting work that was done, but most of the grouting work was to water tighten the joints. So no, there wasn't a huge amount of work done to the existing structure apart from cutting it down so that they could redo a double curvature. In terms of the contract, the engineering contract between us and Nant de Drance is it's an SIA 103 type contract, so it's a standard Swiss engineering contract, and it's by the hour with several levels of caps. So you have a certain hourly rate till you get to a cap, and then after which you get a penalty, and after which we have a certain amount more, and then you have another penalty. So the idea is to kind of have a limit on how much the engineer can spend, if you will.
Questions, yeah? Do you want to pass the mic down?
Patrick, first of all, I'm gobsmacked at the scale of investment the Swiss seem to be more than able to afford. But how many?
See my taxes.
So you'll fit back in very well when you return to us here, will you? How long did it actually? What length of tunnels actually were bored as part of that project, and how long did they actually take, just at a very macro level, to get an idea of the scale of tunneling that was actually
Overall, it's about 15 kilometres of dry tunnel and 2.5 kilometres of wet.
And it took how long?
Well, it started off in 2009, so we saw the drive for the tunnel boring machine start off in November 2009, and they also started at the upper level at the same time in order to have a reception cavern when the tunnel boring machine arrived. And excavation finished off about 2014, I imagine 5 years.
5 years. And sorry, the wet tunnels, what length of wet tunnel did you say?
I think it's about 2.5 kilometres.
2.5 kilometres. Very impressive.
Yeah, like, you know, the reservoirs are finally quite close together, so, you know, the amount of wet as opposed to dry is quite small.
Thank you.
Eamon Stack, Banner Precast. Did you say that the TBM, was that the actual machine that did the recent Lutchberg tunnel?
Yes, one of them. There
One
were
of them.
4 on the Logistical tunnel, I think.
Yeah, recycling. Yeah.
Oh yeah, like they get recycled a lot.
Yeah. And then, sorry, on the heightening the dam, does the dam actually behave like a horizontal arch? Is that the idea?
Yeah, exactly.
Okay, thanks.
What a job to have on your CV for the next job.
I know.
Congratulations to you both on the project and on the presentation. My query really is, was all of the rock excavated of suitable quality to make your concrete? And did you have any spoil to get rid of? And if so, what were you able to do with the spoil? Thank you.
Well, yeah, not all was suitable for making concrete, as well as some of it which was a bit too. I mean, I didn't follow exactly the management of the spoil, but some of it would have been too clayey or whatever. There's also some of it which has too high concentrations in radioactive material, because granites and gneisses in those areas have got uranium in them, and some of them also had too high concentrations of arsenic. So as well as that, we had to find special places to put the contaminated spoil, if you will.
Thank you.
Patrick, sorry if I may have a second question. A very good presentation, thank you. Could I ask you, Patrick, for a pump storage system, is there a cavitation limit for the intake coming in for the pumping from the lower lake?
Unfortunately for that, you'd have to ask AFC, the lead consultant, or the people who designed the electromechanical and who interface with GE. But
no, I understand there is. It was just I was wondering if you might be able to confirm the value. Yeah.
No, I mean I could find out this information.
No, it's no problem. Thank you.
When is the project expected to enter service?
It was supposed to start some stage this year, but unfortunately there were some issues with electromechanical equipment, which pushed back the start of commissioning by 18 months. So in particular, what happened was the spiral casings in which the wheel was going to go need to be concreted in place, but before that they need to be checked so that they don't have cracks in them. And when they arrived on site in January 2016, 4 of them were found to be defective, and after 6 months of repairs it was decided to scrap them and start again. So now it's expected to, wet commissioning is expected to happen between mid 2018 and mid 2019.
How's the project faring against budgets set out at the beginning?
In terms of the cost?
Yes.
Well, I could say quite badly, but it's not exactly true. Originally, it was set off as a 600 megawatt project, and then the financial situation changed. Namely, the large-scale subsidy of renewables in Germany meant that the price of electricity on the European market went crashing, which meant that in order for it to be financially viable, Nant de Drance had two options: either they shut down the project or they increased it by 50%. So what they decided to do, since they were already that far into the project in 2010 or 2011, they decided to order 2 more groups off Alstom and increase the size of the powerhouse and heighten the dam. So in the original concept, the heightening of the dam wasn't included.
And as far as you know, does the project stack up economically still?
No.
No.
But I would say that that's a short-term economic view, and that's probably where pumped storage is maybe often looks like a red herring, because you need large upfront investment, and over its lifespan, this is something which is going to last 100 years. It's probably going to recoup its value many times, but the upfront costs are generally quite prohibitive. Yes.
Thanks.
Just a quick one. Just curious, the turbine supplier, was it GE or Siemens supplied the turbines?
Everything inside the powerhouse is GE.
Thanks very much for that, Patrick. Just going back to one of your earlier described slides, the Swiss situation similar to Ireland, in that
Yeah.
most of the renewable sources in Switzerland being hydro in unpopulated areas in the south. What were the requirements and kind of the public acceptance of grid connections for those, with say 3 new major hydro schemes?
You mean the grid connections themselves, the high voltage cables?
High voltage underground, overground, and
Yeah.
fairly scenic areas. What's the Swiss comparison with what we experience in Ireland?
Well, I haven't lived in Ireland for 10 years, but I know it's a sensitive subject. It's also a sensitive subject in Switzerland, where people living in the valleys with hydropower plants all over the place are getting a bit sick of having yet another high voltage line being put up in front of the house. So for Nant de Drance, there's one 380 kilovolt line which needs to be brought down to the valley, and that is overground until you get to the valley, and then it had to be put underground. So there's they're actually digging using a micro tunnel boring machine, an underground system. Yeah. So in terms of acceptance, yeah, it's getting more difficult. Yeah.
Thank you very much, everybody, for coming this evening. Our next talk, I've forgotten what it actually is, but it's on the 19th of April. So apologies, but it's on the event calendar, and it's JP Rooney will be speaking, and he's from ROD, and it's to do with water, but it's on the event list. All right. Thank you very much, everybody, and good evening. Thank you.